Hello, everyone. I am Ahmed Mahmoud from DataMindAI, and I'm the head of data and AI engineering. Uh, Today, we are going to talk about something that has genuinely changed the world in the last 2 years, the large language models, or LLMs, they call them. Now, I'm sure you have used ChatGPT or Claudia or Gemini in the last week. And probably you might have wondered what is happening behind the prompt. So, so today, what we are going to do is we are going to close that gap, the gap between what you type and the tool behind it. And between the gap between using these tools and understanding them, exactly why we are here today. And at DataMind AI, we sit at the intersection of four disciplines: AI, data analytics, data engineering, and decision science. And I can tell you from the front line, no technology in the last decade has touched all four of those areas as profoundly as LLMs have. Whether you are building pipeline, analyzing data, designing AI product, or making strategic decisions, you need to understand this technology, not at the surface level, but deeply. So today we are going to do three things. We are going to demystify what these models actually are. We are going to understand how they work, and we are going to look at what that means practically for your work, your organization, and your career. I will move fast. I will be specific, and I will call out the things that the textbooks are not explaining properly. Let us go. Today, we are going to build something together, a precise, technical, accurate mental model of large language models that you can use in your work immediately. So let me start with a simple question. How many of you have used the phrase artificial intelligence in a meeting in the last 2 weeks? Now, how many of you, if pressed, could give a technically precise definition of what AI actually is? Not the marketing answer, not the science fiction movie answer, the real definition. Now, that gap between using a word fluently and understanding the concept precisely is a professional liability in 2025. Not because people are unintelligent, but because the word AI is doing an enormous amount of conceptual work in our industry, and it is doing almost none of it accurately. Yeah? The word AI gets applied to a thermostat with a schedule, to Netflix recommendation, to ChatGPT, and to the autopilot in a commercial aircraft. Those are radically different systems with radically different architecture, cost structure, failure modes, and governance requirement. If your CTO says we need AI in our product, and you don't understand which of those four levels they mean, you are going to build the wrong thing. Today, we build the vocabulary. We are going to establish the hierarchy where AI ends and machine learning begins, where deep learning fits, and where large language models specifically sits. And we are going to do it with enough rigor that you can explain it to a non-technical executive and defend it in a technical architecture review. As I said before, DataMindAI sits as an intersection of four disciplines: AI, data analytics, data engineering, and the decision science. And every single one of those disciplines has been transformed by LLMs in the last 24 months. Understanding this technology is not optional, but for everyone in this room. Let us begin. The AI layer, the hierarchy. Yeah. So probably you have seen a lot of diagrams similar to what I'm producing here. Some of them in boxes, some of them in circles. But the single most useful mental model for understanding this technology is a set of boxes, whether they are nested boxes, each one a subset of the one outside it. So let me walk you through each layer. The outer most box is the artificial intelligence. So AI is the broadest category. Any technique that allows a machine to perform tasks that would normally require human intelligence. Yeah? Notice what that definition does not say. It says nothing about data, nothing about learning, nothing about neural networks. For example, a chess engine from 1997 built entirely from hand-coded rules, hundreds of thousands of if-then statements written by chess grandmaster is technically AI. So is like a spam filter built from regular expression so that it filters whether an email is like a spam or not. Yeah. So it's a simple decision tree. Now, this is the AI. Now, the second, the first inner layer is the machine learning, the first narrowing. So inside AI sits machine learning. Yeah. So the critical distinction here is instead of programmer writing explicit rules, the machine learns rules from data. Say, for example, the program if then kind of thing. The programmer writing the explicit rules, the machine learns from data. You show it thousands of examples, it finds the pattern itself. Yeah. So real example is Netflix. Yeah. Recommendations. Nobody at Netflix wrote the rule. If a user watched, for example, Succession and The Crown, he recommended Diplomat, for example. Yeah. So the machine learning system learned those correlations from 230 million viewing history. It found connections no human would have thought to encode. That is a machine learning. Now, the deep learning, the second narrowing side, is inside the machine learning itself. There is a deep learning, a specific family of algorithms using neural networks with many layers. Before deep learning, a data science had to manually decide which feature to give the model. For image recognition, you would manually define, look for edges, look for curves, look for shapes. Yeah. Now, deep learning learns these features automatically from raw data. So the ImageNet moment in 2012 changed everything. A deep neural network called AlexNet reduced image classification error by 41% in 1 year using features it discovers entirely on its own. That single result triggered the modern AI race, which is the large language models, the innermost box. So they inside deep learning sits large language model, a specific type of deep learning model designed for languages using a particular architecture called the transformer, trained in massive text corpora. So the deep learning revolutionized image processing, while the large language model now revolutionized text processing. Yeah. So the key navigation principle is every LLM is a deep learning model, which is a machine learning model, which is AI. Yeah. So let me repeat this one. So every LLM is a deep learning model, which is a machine learning model, which is an AI. But not every AI system is an LLM. When someone says we are using AI, ask which layer. The answer determines build complexity, data requirement, cost, and governance requirement. Now, slide 3 tells you how a machine actually learns from data. We will use a concrete example that has nothing to do with language, deliberately because the intuition carries all the way up to GPT-4. So what is the machine learning? So I'm going to spend a little bit of time here. I want to use an example completely unrelated to language because I want you to build the core intuition before we add the complexity of text. Imagine you work for a music streaming service. Your job predicts whether a new song will be popular before releasing it. You cannot listen to every song manually. You get 5,000 submissions per week. You need a system. A traditional programmer would try to write rules. If tempo is between 100 and 130, BPM and the chorus arrives between 45 seconds and it follows verse chorus structure, then predict popular. But who decide those thresholds? What about slow ballet that went in viral? Trap songs, rules break down immediately. The machine learning approach instead takes a historical data set of, for example, 100,000 songs, and for each song, record measurable features like tempo, duration, danceability, score, energy level, key signature, major versus minor mode, seconds until first chorus, whether it has a recognizable hook. Record the outcome. Did it becomes a hit or the outcome now? This is the key part here, the label we call it. Then it records the outcome. Did it becomes a hit or not, based on the criteria. Now feed this to a learning algorithm. The algorithm finds the combination of features that best predict the outcome. It might discover that a specific combination of high danceability plus medium tempo plus chorus within 28 seconds predicts popularity with 73% accuracy. A combination no humans would have included as a rule because no human analyzed 100,000 songs manually. Now, when a new song arrives, extract its feature, run them through the trained model, get a score 68% likely to be popular. The number came from patterns in these 100,000 examples, not from a rule, but from data. So why this example matters for LLM? The core mechanism in GPT-4 is identical to this, just a scale that makes the song example look trivial. Instead of 100,000 songs and 10 features, now trillions of sentences and billions of learned parameters. Yeah. So instead of predicting popular or not, it is predicting what is the next word in this sequence. But the fundamental loop, present examples, measure predictions error, adjust parameters to reduce that error, repeats billions of times, is exactly the same. There is no magic. There is pattern recognition at a staggering scale. So correlation, not understanding. So this matters for how you use and trust these systems. I, a, a machine learning model does not understand the data. It learns a statistical correlation between inputs and outputs. And some popularity models trained only on uh, 1980 rock will learn that electric guitars correlate with hits, not because that is universal true, but because it was true in its training distribution. When 2000s hip hop arrives, it fails. This is called distribution shift, and it is not. It is one of the most common failure modes in production AI systems. Now, let us take a step back and ask the most fundamental question. How does any machine make sense of the world? Everything a computer processes is ultimately a number. So let us see this for images first, because images makes beautifully transparent before we tackle the much harder problem of language. Now, from pixels to numbers. So here is the single most important conceptual bridge in all machine learning. Computer operates on numbers, only numbers. Everything else, images, sounds, words, videos, must be converted to numbers before any learning can happen. For images, this conversion is transparent and intuitive. Take a digital photograph, zoom in far enough and you see individual pixels, tiny colored squares. Each pixel has a color. Each color is represented by exact three numbers: red from 0 to 255, green from 0 to 255, blue from 0 to 255. So black is 000, white is 255, 255, 255. Pure red is 25500. A warm orange is approximately 255, 140, and 0. Now, a standard HD image, which is 1920 by 1080 pixels, is a grid of 2,773,600 pixels. So each pixel has three numbers. The entire image is therefore represented as a list of 6,220,800 numbers. That list is what the neural network sees. That is all it ever sees. Why this solved a hard problem before deep learning? If you wanted a computer to recognize a cat in a photo, a computer vision engineer had to manually describe what a cat looks like in a mathematical terms. Look for two triangular regions in the upper portion. Look for whisker length, horizontal lines. Look for fur-like texture pattern. This is this was called future engineering. It was a fragile, labor-intensive, and failed when the cat was photographed from an unusual angle or unusual lighting. So deep learning breakthrough, given enough labels, examples, enough images labeled, for example, cat or not cat, the network learns what features to look for automatically from the raw pixels numbers. Nobody told AlexNet to look for ears. It discovered that certain pixels pattern in certain position correlate statistically with label cat. This is what learning from data means concretely. Yeah. Now, this pixel to number pipeline is clean. The conversation is lossless. No information is lost. Language does not have this property. Converting words to numbers in a way that preserves meaning is much harder problem, and solving it requires a decade of research. But the goal is the same: find a numerical representation rich enough that pattern in that representation correspond to pattern in meanings. Now, if the room has a mixed technical background, ask what happens to the pixels numbers if you rotate the image 90 degrees. The answer is they change completely. Same cut, different numbers. Is a good preview of why language is harder. Dog bites man and man bites dog have the same words but completely different meanings. Similar to rotation problem but harder to solve. Now, images are clean. The conversation or the conversion from image to number is direct. Language is far messier and far more interesting. So let us look at the specific challenge of turning words into numbers in a way that preserve meanings. Now, from words to numbers, I'm going to spend a bit of time here to get it right. Most people, if asked, would say it is harder to teach a computer to recognize a dog in a photo than to understand sentences. I need a word that means happy, but more intense. They would be wrong because language is significantly harder than images. And here is a problem or the challenge. Challenge number one is the variable structure. For example, an image 256 by 256 image is always 65,536 pixels, yeah, times the 3 channel for color. Now, each input has identical dimensionality. You can compare images mathematically in a consistent space. Language has no equivalent structure. So sentences vary from 2 words to 200, yeah? Documents vary from 1 paragraph to 1 million words, yeah? Neural network prefer fixed size inputs. Handling variable length sequences required entirely new architecture ideas. Now, challenge number two is the vocabulary explosion. If you want to convert every English word to a unique number, you would need an entry for all the 600,000 plus words in the English language. But what about color versus color? Color with the COLOUR versus the COLLOR without you. What about Chat GPT, a word that did not exist before 2022? What about medical jargon, legal Latin, brand names, acronyms, emoji, code identifier? A fixed word level vocabulary constantly goes out of date and completely fails on any unseen word. Now, challenge number three is context dependency. This is the deepest challenge. A pixel that is RGB, for example, like 200, R red is 200, 50 is green, 50 is blue, means the same color regardless of what surrounds it. But the word bank, for example, means something completely different in I deposited money at the bank versus I sat on the riverbank. Same 4 letters, completely different meaning. The meaning of a word is determined by its context, by the word surrounding it, so not by the word itself in isolation. A naive approach assigns each word a unique ID from 1 to 600,000, loses all of this. It cannot handle new words. It treats good and excellent as completely unrelated, different ID numbers with no relationship. It cannot handle context dependency. Now, the solution is hierarchy. So the field solved this in stages. First, tokenization, break words into subword units that balance vocabulary size with coverage. Second, embeddings. Now, represent each token as a vector of numbers in a high dimensional space where similar meaning cluster together. Yeah, so this is the embedding. So the tokenization breaks the words into subwords which balance again vocabulary size with coverage. The second important stage is the embeddings, represent each token as a vector of numbers in a high dimensional space where similar meaning cluster together. Yeah. Third is like contextual embeddings. The transformer computes different embeddings for the same word depending on the surrounding context. Now, bank in a financial sentence and bank in a geographical sentence have different embedding vectors. Yeah. So we'll cover each of these in details, but the key insight here is the challenge of words to numbers is not a minor engineering details. It is the central problem of natural language processing, and the solution, the transformers with contextual embeddings, is what makes LLM so capable. Now, the next slide, let us make this challenge a bit concrete with a specific task, sentiment analysis. It is the perfect teaching example because every human in this room can do it intuitively. And teaching a machine to do it reveals every fundamental challenge in language processing. Sentiment analysis determine whether the text is positive and negative or neutral. Is a perfect introductory NLP task. Every human in this room can do it in a millisecond. Teaching a machine to do it reveals every fundamental difficulty in the language processing. So let us see it in example. For example, the obvious case, example number one, the keyword counting works. So, for example, the film was absolutely wonderful. The performance were outstanding, and I was genuinely moved. So if someone is asked you to do this analysis, or if you give it to a machine, so what you can do here is like for the sentiment analysis, um, you count the positive words. For example, positive is like words like wonderful, outstanding, moved, and are unambiguous positive signals. A simple keyword count now can work because count positive words from the sentence, count negative words again, and take the difference. And the result would be whether the sentence is positive or negative. So if there was more positive words, then you would say the sentiment was positive. It was more negative, say the sentence was negative. Yeah. So this is like very obvious by counting, but the counting also breaks, like in this example. For example, the acting wasn't bad and the story wasn't entirely unengaging, though I wouldn't say I loved every moment. So here you might call it mildly positive, but looks at the structure, wasn't bad is a double negative, meaning acceptable. Yeah. And wasn't entirely unengaging is a triple negative, meaning somewhat engaging. Yeah. I wouldn't say I loved it means is is a negated positive, meaning I liked it, but not that intensely. Yeah. But now a keyword counting sees bad and engaging flags this as a negative. Wrong. The model must understand that wasn't negates the word that follows it. Yeah. So that the scope of negation matters. So that hedging language signals moderate positive sentiment. These are syntactic and semantic phenomenon, not a keyword phenomenon. So let us see, for example, this is again a very good example. Example number 3 is sarcasm requires word knowledge. So, oh, brilliant. my flight was canceled, my luggage lost, and they gave me a £5 food voucher. Exceptional service. So sentiment here is strongly negative, but brilliant and exception are positive words. A model without world knowledge, without knowing that cancelled flight and lost luggage are bad outcomes, and that £5 is insulting compensation, will classify this as positive. Understanding sarcasm requires recognizing that positive words in context of obviously negative events signals irony. Knowing what the events are and whether they are good or bad, understanding that the escalating list of misfortunes followed by a compliment is a common sarcasm pattern. Now, modern LLM handles all these examples correctly, not because they were programmed with sarcasm rules, because they have read, but because they have read millions of sarcastic sentences in context and learned from that statistical signature of irony from training data. So the business context here. The business context here, Amazon processes millions of product reviews per day. Say, for example, Amazon processes millions of product reviews per day. They use fine-tuned LLMs for aspect-based sentiment analysis, identifying not just overall positive, negative, but which specific product features the sentiment refers to. The battery life is excellent, but the camera is disappointing is one review with mixed aspect level. Sentiment analysis, human annotation at that scale would cost tens of millions per year. LLMs do it for a fraction of a cent per review. So next time we are going to look in much details the challenge or on a different level, and you will see tokenization. It's from words to numbers. We are going to talk now of tokenization. This is the first stage, as we call it, in LLM. So we established two things. We cannot use full words because vocabulary is too large. Yeah, fails on new words as well. So you cannot just use the full words now, and you cannot use individual characters as well because sequence too long, patterns too distant. So tokenization is the middle ground and is more cleverly designed than it first appears. Now, you have this BPE algorithm. The most widely used tokenization algorithm is byte pair encoding. Byte pair encoding, BPE for short. It starts with individual characters and iteratively merges the most frequently occurring pairs until reaching a target vocabulary size, typically 32,000 to 100,000 tokens. So working example, what actually happens is, for example, unbelievable. You have the UN, the believe without believe and able. So 3 tokens. Why? Because un appears as a prefix in thousands of English words. Yeah, uncertain, uncomfortable, unhinged. Yeah. Able appears as a suffix in thousands of words as well. So comfortable, remarkable, achievable, and so on. Believe is a common root. Yeah. So the model has seen all these fragments in many other contexts. So even a word it has never seen as a whole can be processed from this familiar subcomponent. Yeah. Now, Chat GPT is like Chat G and PT, a word that didn't exist before 2022. The tokenizer handles it gracefully by decomposing it into fragments it knows. Without tokenization, ChatGPT would be a completely unknown token the model could not process at all. So, for example, code example is print for example, in Python is typically a single token in models trained heavily on code. Because this sequence is so frequent that BPE merges it. This is part of why LLM are unusually capable at Python. Python has highly repetitive, regular syntactic pattern that compress well. So, for example, numbers so 1, 2, 3, 4, 5, 6, 7, 8, 9. You have 1, 2, 3, 4, 5, 6, 7, 8, and then 0. 4 tokens split at arbitrary boundaries. This has a direct implication. Arithmetic with large numbers is genuinely hard for LLM because numbers are fragmented into pieces with no inherent numerical relationship. The model does not process 1, 2, 3, 4, 5, 6 as a number. It processes 3 separate tokens. Yeah. So three practical implications for everyone in this room is first, billing. So API providers charge per token, yeah, not per word. English average 1.3 tokens per word. So the average English language, say for example, if you are going to do cost analysis in this in LLM, you need to know the token, and a word, for example, in English is approximately 1.3 token. Yeah. So code averages 1.5 to 2.5 tokens per word due to symbols and brackets. Yeah. So if it's a code, it's slightly different, 1.5 to 2.5. And then a 1,000 words document is roughly 1,300 input tokens. Yeah. So that's second, context limits. The context window limit is in tokens, not words. Say, for example, a 128,000 token context window holds approximately 96 English words, about the length of a full novel. Yeah. So when they say context window of 128,000 token, for example, yeah, now it is 96,000 English words, and 96,000 English words is about a full novel. Yeah. Third, prompt efficiency. If you are near a context limit, yeah, more concise prompts use fewer tokens. At scale, token efficiency is directly proportional to cost efficiency. Yeah. Now, that this area is very interesting side. So let us now go to the second area of we saw like tokenization solves the vocabulary problem, but we still have not solved the meaning problem. Yeah, the meaning problem not solved. The vocabulary problem, we resolve it now. A token ID is just a catalog number. It carries no semantic information. Converting tokens ID into rich representation of meaning is what embeddings is do or can do. Yeah. So let us see on the second side of the word embedding. After tokenization, each token has a unique ID. Yeah. So a position in the vocabulary, but token ID 4521 is not more similar to token ID 4520. That's than it is to token ID 9. The numbers are labels. They carry no semantic information whatsoever. We need to convert each token into representation that captures its meaning. It is relationship to other words, for example. It is typical context. It is semantic category. That representation is called an embedding. A vector of numbers, typically 300, 384 to 4096 numbers long. That positions the token in a high dimensional meaning space. So the geometry of meanings. Here is the remarkable property of embeddings. Similar meanings cluster near each other in this high dimensional space. For example, doctor, physicians, surgeons, nurse have embedding vectors that are close together. Yeah. So dog, cat, hamster, and goldfish cluster in another region. Paris, London, Tokyo, and Berlin cluster yet in another one. Now, and in the relationship are genuinely geometric. The famous example is a vector for king minus a vector for man. Yeah, plus the vector for woman gives you a vector close to queen. Yeah, let me repeat this one. So the vector for king minus the vector of man plus the vector for woman gives you a vector close to queen. Embedding space has captured the concept of royalty as a direction and gender as another direction, and you can navigate between them alphabetically. So king minus man plus woman equals queen, Paris minus France plus Germany. Yeah, is almost equals Berlin. Running minus run plus swim, for example, is equivalent swimming. This is not programmed. It emerges from training a model to predict which words appears in similar context. Now, doctor and physicians appear alongside patient, hospital, diagnosis. So similar context. So their vector converge. Meaning is learned indirectly through this occurrence statistics. So how embeddings are learned? The embeddings are not handcrafted. They are learned during the training. The model starts with random vectors for every token. As it trains on billions of examples predicting the next token, it adjusts those vectors until tokens that appear in similar contexts have similar vectors. Yeah. So the geometry of meaning is an emergent property of the training objective. Now, the 2013 word to vector paper from Google demonstrates this principle by training a simple neural network to predict surrounding words from a target words. They obtained vector with these algebraic properties. Modern LLM embeddings are much richer, higher dimensional versions of the same core idea. Now, the practical implication here is the semantic search. Embeddings are used directly in semantic search, the backbone of modern RAG systems. Instead of keyword search, which requires exact word matches, semantic search converts queries and documents into embeddings vector and finds the nearest neighbors. So search for heart attack will return results containing myocardial infarction, even without any keyword overlap, because those phrases have similar embeddings vectors. This is how enterprise LLM applications make documents searchable without requiring users to know exact terminology. Now we can assemble the full pipeline from raw text input all the way through to the output. Let us walk through exactly what happens when you type a prompt and press enter. So the complete pipeline now. Let us walk through exactly what happens step by step. When you type a prompt into an LLM, every step matters, and knowing the pipeline helps you understand the failure models or the failure modes, as it were. Now, step number one is tokenization. So your raw text is split into tokens. So I love this movie. It becomes 5 tokens. And then and then space, and loved this movie exclamation mark. Each token is mapped to its vocabulary ID. Say, for example, the ID 46091, 428, 3807, and 0. So this is the token now. Yeah. Step number 2 is embedding lookup. So each token ID is converted to its embedding vector. For example, token 6091, the word loved, yeah, becomes a vector of, say, 768 numbers encoded its position in meaning space, yeah. So 768 numbers encoding its position in meaning space. We now have a matrix, 5 rows, 1 per token, yeah. Now 768 columns, yeah. This is the actual input to the neural network. Now, the 768 columns we're talking about is like it describes it tries to look at the word in a different context, yeah. Whether it is human, whether it is space, whether it is emotion, whatever. So each column asks a question, and the answer for that question, look at this one, yeah. So the answer for that question specifies the number you get, yeah. So step number 3 is positional encoding. So the transformer processes all tokens in parallel, yeah, but it needs to know their order. A positional encoding is added to each embedding that encodes position 1, 2, and 3, and so on. Without this, the dog beat the man and the man beat the dog would look identical, yeah. So the positioning is also important, yeah. So the positional encoding preserves word order in a parallelized architecture. Now, the step number 4 is a transformer layer, of course. So the embedded position encoded tokens pass through multiple transformer blocks, typically 12 to 96 layers for modern models. In each block, self-attenuation attention lets every token consider every other token's context. Yeah. A feed-forward network applies a nonlinear transformation. Layer normalization stabilizes the training. After each layer, the representation become progressively richer and more contextual. So each layer encode the surface feature, later layers encode task level semantics. Now, step number 5 is the output prediction. After the final transformer layer, the model generates a probability distribution over every token in its vocabulary for what should come next. Paris might have probability of 0.97. Leon has a probability of 0.02. So everything else shares the remainder. So the model selects the highest probability token or samples from the distribution if temperature is greater than 0. So the generation loop is this selected token is appended to the context. The entire process runs again, and now with one more token in the input, this autoregressive loop continues until the model generates a stop token or reaches a length limit. A 300-word response involves 300 plus iteration of this loop. Now, the tokenization output token ID are converted back to text. The user sees the readable input, yeah? So you remember we converted token ID. So that ID is like a representative token. So now you convert it back to the token from the ID. So the scale reality check. So GPT-3 has 175 billion parameters. Processing a single 1,000 token prompt requires approximately 350 trillion floating point operation just for one forward pass. So an NVIDIA H100 GPU performs about 2,000 trillion such operation per second. So even with this, generating a multi-paragraph response requires multiple GPU working in parallel. Now we have earned a precise definition of what a large language model actually is. Let us state it clearly and then unpack every part of it. So next time, the transformer is a bit complex idea here. So I'm going to spend a bit of time or another session about the transformer itself, explain how it works in actual things. But here, the whole idea is the language model, the complexity, the steps it requires. It might not be necessary to understand exactly how the transformer works at this stage. What what you need to do to know is like the actual step-by-step process and where it goes and what happens, and then you get the output, and then after the output you have the from the token ID. You start from token ID, and then you end up with the tokenization, which means you return it to a text. Yeah. So we will look at the transformer side because it was so difficult to present it in a very short session like this. Yeah. Now we came to these questions. What is an LLM then? So we have now earned a precise definition. Let me state it now. A large language model is a deeper neural network. Yeah. So this is the key part. It's a deep neural network, specifically a transformer trained via self-supervised learning on a massive text corpora using a next token prediction objective, producing a system whose learned parameters encode statistical representation of the language, so world knowledge and reasoning patterns sufficient to perform a wide range of tasks without task-specific retraining. Now, let me unpack each component. So deep neural network is specifically a transformer, multiple processing layers, self-attention at each layer, learned representation that deepens with each layer. Now, this is the deep neural network here, the transformer. Now, the second bit is the self-supervised learning. No human labels required. The next token is always available at the correct answer. The training signal comes from the data itself. Now, this self-supervised learning is interesting. Yeah. So drones these days uses this self-supervised learning, or like a driverless taxi, for example, or cars also use this self-supervised learning. So behind the scene of this LLM, there is this self-supervised learning. So you don't need human labels required. So the next token is always available at the correct answer. Yeah. So the training signal comes from the data itself. Yeah. Now, massive text corpora. This is the third element. Now, trillions of tokens from web crawls, books, code, academic papers, legal documents, Wikipedia, more text than any human could read in thousands of lifetime. So this massive text corpora it's so difficult even to imagine because if you see libraries and the internet, the web itself, and the books, the academia papers, the legal documents, and even the Wikipedia itself is a huge text which is being used to train the large language model. Now, next token prediction objective is the only training task. Predict the next word. Yeah, that is a task of LLM. So predict the next word. Everything else is emergent from this. Yeah. So the other one is encoded statistical representation. The model does not store facts like a database. It encodes patterns, the distributional properties of language as 175,000 billion numerical weights. Yeah, 175 billion numerical weights. Paris, the capital of France, is not a row in a database. It is a configuration of parameters such that the capital of France is reliably followed by Paris. Yeah, so that's how it is encoded statistical representation. So you have this wide range of tasks without task-specific retraining. Also, this is the key capabilities. One model trained once can summarize, translate, classify, generate code, answer questions, write poetry. This generalization distinguishes LLM from all previous generations of narrow AI. Now, the emergence phenomena here is what supervised or here is what surprised everyone, including the researchers who build these systems. A certain scale, roughly 100 billion parameters, models began exhibiting abilities they were never explicitly trained for. For example, translations ability in languages barely represented in training data. Can you see it? Translation ability in the language barely represents in training data. Multi-step mathematical reasoning, code debugging, analogical reasoning across domains. These abilities were not programmed. They appeared suddenly at certain parameters. Yeah, like water turning to steam at exactly 100 degrees Celsius. So all this code debugging, analogical reasoning across domains, mathematical reasoning, all this stuff came when this ability was not programmed. They appeared suddenly at certain parameter scale. This is called emergent capabilities. Below a threshold, an ability is absent. Above it, it is suddenly present. We do not fully understand why this happens. It is one of the most active areas of AI research. Yeah, and one of the most important open question in science. So this is very important idea. So you see certain phenomenon, certain aspects of features appear at certain scale. Now let me repeat this one because this is very important. Yeah, it is called emergent capabilities. Yeah, so if there is below certain threshold, yeah, an ability is absent. Above it, it is suddenly present. So that's the key part. So there is a threshold which makes something appear. So for AI, for LLM, what we saw before was like a couple of capabilities. Like for example, roughly they found out 100 billion parameters. So when you reach 100 billion parameters, so the models began exhibiting abilities they were never explicitly trained for. Yeah. So this is the threshold. Below that, you don't see that. Above that, you see. So translation ability in languages. Yeah, this is one. So when you reach like 100 billion parameters, you see the capability of translating a language. Now, multi-step mathematical reasoning, code debugging, analogical reasoning across domain. These are capabilities which appears when we reach like 100 billion parameters. I think if you can take this one, and if you are doing research, you can do more research on it, and probably you can enlighten other people on that aspect. Summary and the key takeaways from today's session. Let us crystallize everything we covered today into 5 things you can use immediately. Takeaway number 1 is AI is a hierarchy, not a monolith. Yeah, LLM is inside deep learning, inside machine learning, inside AI. Be precise about which level you are discussing. The implication for build complexity, data requirement, governance, and cost are radically different at each level. When someone says we need AI, ask which layer and why not a simpler one. Number 2, takeaway number 2 is machine learning. Machine learns from examples, not rules. Yeah. So the core machine learning loop present examples, measure prediction errors, adjust parameters, repeat. This loop scales from predicting song popularity to predicting the next word in a trillion token corpus. Yeah, the mechanism is identical. There is no magic, only pattern recognition. So the core of machine learning loop is that you present an example, measure prediction error, adjust parameter, and repeat the usual. Yeah. So give it example, measure prediction error, adjust parameters, and repeat. So this is what happens everywhere, and so this is only pattern recognition at different scale. Yeah, so that's the key part. Takeaway number 3 is like language requires special representation. For example, raw words cannot be fed to a neural network. They must be tokenized into subwords unit, converted into embeddings vectors that encode semantic meaning geometrically and augmented with positional information. So the quality of this representation pipeline directly determines what the model can learn. Now, takeaway number 4 is the transformer process all tokens in parallel via attention. So this is a key part. So transformer process all tokens in parallel via attention. So unlike LR sequential architecture, self-attention lets every token directly reference every other token. Yeah, capturing long-range dependencies that previously or previous modules missed. Yeah, so this is why transformers outperformed everything before them on nearly every language task from 2017 onwards. So takeaway number 5, this parallelism is a key part. So this is the transformers process all tokens in parallel, yeah, via attention. So that's one. And takeaway number 5 is LLM are next token predictor with emergent capabilities. So LLM, if just very precise job of LLM is to predict the next token with emergent capabilities. Yeah, this is the key part. So the training objective is simple. The result, a system that can reason, translate, code, and summarize without task-specific training is a profound and not only full understood. Emergent capabilities appear suddenly at certain parameter scale and were not predicted in advance. So what comes next? In the following session, we go deeper. We will look at how training works at scale, the hardware, the cost, the data pipeline, the alignment process, the turns a raw language model into something deployable. We will compare the top models in production and discuss how to choose between them. So any question before we continue? I particularly want to hear if the pipeline diagram was clear. That is mental model of tokenize, embed, attend, predicted, de-tokenize. Yeah. Again, I want to repeat this one. You need to tokenize first, you embed them, you attend them, and then predict and de-tokenize is one you will use constantly as we go deeper. Thank